quantization as such, I think it's so essential, especially when we are moving towards the edge, and also when we are trying to reduce model size as such. So, going to start off with introduction to quantization in TensorFlow Lite. So, a little bit about me. So, I did my graduate studies at NUS, that National University of Singapore, and my master thesis was actually around using edge computing for solar energy applications. And apart from that, I also work as a Women Who Code Leadership Fellow. And yeah, my research was mainly around deep learning and smart grids. And previously, I worked as a research engineer at Sama. And currently, I also did a course with Udacity called Intel Edge AI for IoT developers. So let me move on. Here is a quick update. I really wanted to know if someone had a chance to maybe go through a paper, stumble upon one, or like, where are we at this? Like, would you need us to help you guys out? Let me go ahead and see the chat so I can see. Nice to know that this time works for some people. Did you guys, so one of the things why we want to take up this paper reading as such is we realize that a lot which goes on in the deep learning world, in essential news reporting as such, um, at the end of the day, we news reporting, what I mean out here is like, what are the new things coming around? How do we come to know about it? Is through papers. What really happened? How did they end up doing it? So even if you look at Google, right, they'll always release a blog, and in the blog they'll link their paper which is on archive or something. So we did share this homework last time, but in case you guys haven't come across it or didn't have time to read it, it's completely fine. We do have like, it's like, we I'm sorry, Soham, you're only sharing it to the panelists. You have to do all panelists and attendees. Yeah.
My bad. Okay.
Yeah, but so hi Joe. So today is not the first session. We actually had like 2 sessions previously, and we want to understand more about this deep learning space. And one of the things that are required to understand that is that we need to work towards reading papers, and that's I think quite essential. Like a lot of us in the industry keep forgetting that that is what is like, plants to seed into what it comes next. So I think we definitely need to start reading papers. And I know paper reading is quite difficult, and that's something that Soham and I discussed over and over again, is that it's there are several techniques for doing so, and usually no one gets it right. And it's like, it's a gradual process of trying to read and to understand and so on. So what I want to say out here is that we want to give you a chance to read papers, and we want to do it as a group too. So in case if you guys are interested, maybe we can do a paper reading session together. Maybe pick up a paper which is quite interesting and common, and then we can read through it. And what we're hoping out of it is that at the end of the study group as such, or the series that we're doing, we'll have like, a lot of sessions on edge computing for sure. But at the end of the day, we also want to impart like a skill, because you could take this and it could help you read the next paper that you come across. And I think, like, especially as I said, in the deep learning world, it's so necessary to read papers. Unlike, I believe, unlike other software engineering fields, ours is much more paper focused, because we have things up and coming every other day. And to really understand what's happening, it's important to read how they came about doing so. So in short, like, I think, like, yeah, sure, we would love to do paper reading sessions with you. We are also doing one with Edge Impulse, towards the towards next to next week, I believe. So what you can do is you can join our session on that. It's going to be on Twitter Spaces, if I'm
Yeah.
not wrong. So, and Twitter Spaces can be used for joining in the session too. So, why don't you guys give that a shot? We're going to be talking about Hardware Lottery by Sarah Hooker. It's much more of it's a much more easier paper to start off with. Maybe so you can post the link onto the chat too. It's a very
Yeah.
easy paper to start off with. So I think like we can start reading papers together, and I think it'll really help us as a group together to move forward and to learn a lot of things in this area. So that's me giving enough rants about paper reading as such, and let me move right into the topic. So what will you be learning today? So I'll be again going over edge computing, advantages of edge computing. This is for people who haven't like joined our previous sessions and are joining this for the first time. And what is the need for reduction of models? How to define quantization, like what do I mean by quantization here, and what are the types of quantization, and how does this int 8 conversion work, and what do I mean by quantization in simple words? Like obviously I'll be going in depth with quantization, but like don't like stress yourself or pressure yourself too much out. Like it took me a long time to even understand what was quantization and why do we need it. And I think like at the end of this webinar or the study group as such, or this particular talk as such, all I want you to do is understand maybe a little about how it works and have the urge to go back and Google a little more or find out what this toolkit does. I think if you are able to do that, then you will take away the most out of this webinar. And the TensorFlow optimization toolkit, it's something we'll be talking about and also be demoing. And what are the post quantization techniques? And one of the very interesting things, which is quantization aware training, which is an addition to post training quantization. So let me begin. So edge computing as such, so what did we learn about previously? We do have an increase in IoT devices, which causes an increase in cloud dependency. So we need edge devices which have basically their own data centers to perform computation. And this sort of computing is that is performed near the data centers at the edge is called edge computing. And the applications are so many, right from security cameras, maybe processing something outside a bank, to self-driving cars. And what are the advantages of edge computing? I guess you already have a question. I'm not able to see it. Are you able to see this?
Yeah. Yes. So the question is, do we plan to talk about Tensor RT, which is exclusively for NVIDIA devices? Um, yeah, I don't think Tensor RT is exclusive to NVIDIA devices, right?
No,
Or am I
no.
wrong?
It's not
And
exclusive, but yeah, it is used by like we can use TensorRT2 for optimization. But I think like TensorRT is like an entire package, right? It does everything for you in terms of optimization. What we want to go into is how does this happen? Because like yeah, TensorRT might support a few things, but in the crux of it, of how quantization really happens, it's through the optimization toolkit. So it's important for us to understand how exactly are they doing quantization before we end up implementing it, because
true.
not every situation would need you to implement all sorts of quantization. You have to make a decision on your own that okay, if I am doing tensor RT, do I really need to do it? Will that actually help me speed that up, or can I be using something from this toolkit and then be converting it? So obviously it's a set of questions you sort of have to ask yourself over time. But that's a very interesting question you brought up. But that's my knowledge on it, that you use TensorRT at a go. I don't know, Soham, have you used it before?
I haven't used it, but I remember you were using it when you were working on NVIDIA Jetson, right? If I'm
NVIDIA.
not wrong.
Mhm.
Yeah. Um, and yeah, my so just to kind of summarize what Archana said, it- yeah, you can use TensorRT, you can use TensorFlow Lite, you can use Intel's OpenVINO to do all of these different quantization, implement quantization in different ways. but it's also important to like understand the theory behind the quantization, which is kind of what we're trying to show today. And then we're trying to give you an example of quantization and how well it works using TensorFlow Lite for today. But yeah, we can do another session on TensorRT as well.
Yeah, definitely.
Yeah.
If it is something that's interesting, we can definitely work on that too. So,
Mm.
just wrapping up or like rewinding into what exactly are the advantages of edge computing. We have reduced latency. We also have reduced internet bandwidth. We have increased security. We have a reduction in the end of the day on cloud services. And why do we need to reduce models? So when we look at a neural network as such, this is coming into deep learning and what exactly comprises a neural network. We know that they have power constraints, which means that for example, we do not fully understand the potential of neural networks until we introduce GPUs. Why did that happen? Is that GPUs were able to parallelize neural networks. And what we realized when we started using GPUs is that they require massive amount of computation and power. But not every device that we want there to be running neural networks on can support such a power and computation constraint, which means that, for example, CPUs and CPUs, I think, have around 140 TDPs of power. But when you go on to smaller devices like a Raspberry Pi or a neural compute stick, it will take around 1 watt. So that's exponentially or like comparatively very, very low. And then obviously, as I said, they require a huge amount of computation, which is like one of the things which is plays at the crux of what we want is the fact that they're composed of floating point values. And you'll see me saying about it again and again because of the fact that neural networks were traditionally built to preserve both accuracy and speed. Hence they were built using floating point values, both float 64 and 32-bit. The memory constraints, when we have laptops and PCs that come with at least 4 GB of memory and we go to a Raspberry Pi, it has 1 GB of memory, which causes us to actually think about inference efficiency, that we actually need to make sure that a the model is of very small size, and what do we do to reduce the size. And at the end of the day, we need to make sure that when we deploy these models onto these small devices, we are able to take less time for inference. So, yeah. So, this is what brings us to now quantization and pruning. So, quantization basically forces the network to simulate in lower bits. This is something which we will be talking about today. But there is another way to reduce your model size as such, which is pruning, which is where you see out here. Let me just, sorry. Yeah. Um, where is the pointer? Sorry, I thought there's a pointer here. Um, yeah, got it. So with pruning, we actually have like these neurons, right? So what we're trying to do is that we force zero interconnection, or what we can think of in some ways is that we are removing connections throughout the network. Ideally, what we do is we remove 20% of it, and then we again notice how the uh, how we are able to perform training. But like in some ways, what you can think about it is we have before pruning and after pruning is that we have interconnections which are removed, and essential the model size is reduced. So let us now move into quantization, which is very interesting and a favorite topic of mine. Is that what do we mean by quantization? So this definition as such came from like a mathematical definition, which means processing, or it's like a process of mapping input values of a larger set of outputs values to a smaller set with a finite number of elements. So what you can think in some ways is that you're mapping a large set of output values to a smaller set in some ways. So this was actually used in mathematics and signal processing as such. But we also quickly realized that this is such an essential tool for to be used by edge in the case of edge computing, wherein it's a process of reducing the floating point 32-bit values to lower precision values, while making sure we are able to preserve the information in the neural networks. So, one of the most interesting points you have to notice here is the fact that it's a floating point 32-bit, and we are reducing it to a lower precision values, which is like maybe floating point 16, or in our case, we'll be focusing on int 8 values. And we're making sure that we're able to preserve the information. I think that's like a very important point out here. We need to make sure that when we reduce the model size, it's able to retain the same information which was there in the start, or retain at least the core information which was there in the start. And so, how do we go about doing it? So, I'm going to do a very quick linear algebra here. It's not going to be super tough. So, let us consider you have neural network weight values. So, these are the weights and the values that are present in the weight. And let us assume that they are from minus 10 to 30. And so the first thing we do is we define the max and the min values. So while doing int8 conversion on quantization, we consider the least value to be 0. And then we consider the maximum value to be 255. Why do we do that? Is 2 to the power 8 is 256. So 0 to 255 essentially makes it 256. And all the values are then scaled in between 0 to 255. So what happens when we want to represent a value like 10.00? So if we remember a bit about our math, we know this value is actually a floating point value. So it's a floating point 32 value. So let us consider this like it's a this is a formula. You don't have to remember it. It's just something out there that I wanted to bring across. So let us say that the old range is equal to the old max minus old min, and the new range is equal to the new max minus new min. Very simple, very straightforward. And then we have the new value. It gets a little tricky here, but I mean, you really don't have to remember this formula. It's not so useful for us, but in essential, it describes the math behind it. So we have the new value, which is old value minus old minimum, and into new range divided by old range plus new minimum. So let us try to do it for our case where we were trying to, for example, have values from minus 10 to 30. And so now what we are trying to do is we are trying to define our old range, which is 30 minus or minus 10, which brings it to 40. And when we look into the new range, this is 255 minus 0, which is another 255, because our new range was from 0 to 255. So our new value, in essential, we want to find out what would happen if we want to define the value 10. Like if we have 10.00 in floating point 32-bit, and we want to have a representation of this value in int8, how would we go about doing it? Then we would have the new value to be this, which is this formula, old value minus old minimum, which is 10 of minus or minus 10. And then, so the old value is 10, right? This is what we want to define. And the old minimum was 10 from previously, into 255, because 255 is our range, 0 to 255 is the new range we defined. And the old range was actually 40 that we calculated plus 0, which is our new minimum, because the least value we took out here was 0. So then we get our answer to 127.5. But again, at the end of the day, it's int8. So we cannot have like floating point values, and we have to round it off to 128. Is that understandable? Maybe I can go over it again.
Yeah, and I just kind of want to say like the math is important, but if you don't understand the math, like basically what we're trying to do is we have like all these weight values in a huge, in a large range as well as large precision, right? Because we can have a value that's like minus 9.3467, and it just goes on. And we're trying to take that huge range and we're trying to squash it into a smaller range. And the formula that Archana is showing here, it's like a very standard formula that takes numbers in one range and puts it in another range. And that's all we're trying to do. We're just trying to squash this huge range that we have into a smaller range. And that's basically what, that's the simplest form of quantization. And even today, like a lot of frameworks and all this, it still uses this way of quantizing because it works really well and it's one of the simplest ways. So Seshu has a question. So does this mean that there's a compromise on accuracy and inferencing? Yes, there is. And there have been techniques to, like there are like a lot of techniques that actually like try to regain this accuracy. And we'll be looking at some of those techniques now as well.
Yep. That's a very interesting question, Zishu, because we actually have, we will be going through ways to actually tackle this. So let me go on to the next slide. So if we look at what do we mean by quantization, like in simple terms, is that we want to make sure that this is something that I came across in, I think, Pete Warden's blog, where he went like, it is not necessary to know how much it's raining outside. If you want to go out for a walk and it's raining, you would just look outside and go like, okay, you don't need to know how many droplets are falling per second. What you need to know is whether it's raining lightly or heavily. So similar to that, we want neural network precisions, which often don't require, neural network predictions often don't require the precision of floating point 32-bit or even 16-bit. So with some effort, we can use 8-bit integers to perform neural network inference and also maintain the appropriate level of accuracy. So this is what we want to go behind. We want to make sure that we are not using higher bit values. We're able to actually convert it to 8 bits and use it. And then comes the question, or then comes the main topic of, TensorFlow optimization toolkit. So what does this toolkit actually comprise of? It contains of tools for doing quantization-aware training, model pruning, post-training quantization. So quantization-aware training and post-training quantization is something that I will be covering up today. But model pruning is something that I believe Soham will be taking up in the next session because it's a very interesting concept on its own. So basically what the TensorFlow optimization toolkit does is that allows you to choose layers you want to quantize in the model. So you're doing like a you're pairing the reduced precision operations, and you're using in essential fixed point and both floating point math. So this is something that's very essential, is that when we talk about conversion, we don't mean that you're converting the entire model. Yes, you can convert the entire model, but we're also providing you, or like this optimization toolkit also provides you to come have something in between, which in essential is like a mixture of both fixed and floating point math. And so what we realize is that we can use hybrid kernels, that we reconvert the parameters to higher floating point values after execution, which means that somewhere in between of this big neural network, we are converting it to 8-bit for doing some sort of computation. But when it comes out to the output side again, we are able to reconvert it back to floating point values. And this in essential is a hybrid kernel, and it works the core of optimization toolkit, TensorFlow optimization toolkit. So what are the types of quantization that we're looking at? So we already have a question. I'm unable to see the questions for some reason.
Yeah. So Seshu asks, why not use the original 32-bit and calculate everything as int, like never use floating point math at all. And also he's apologizing if he's asking too many questions. And don't worry, you're not asking too many questions.
No.
It's all right. So yeah. So people have been trying to like not use floating point 32-bit numbers at all, but it turns out that it's really hard to train networks using integer values. They just don't get the same accuracy. So when you have to train your networks, you have to use floating point 32 bit like weights to train your network. It's only during inference that people have realized that all that precision is actually not required, and as long as you capture the essence of the weights, the model kind of still can predict suitably, like well. It still predicts reasonably well. Um, but what Archana was talking about in the last slide is there are levels to which you can quantize your model depending on your application. So, for instance, you may be deploying your model in, like, say for a company who have like servers who don't need to deploy a model at the edge, but they want to reduce their server costs, and they don't want to and they want to make their inference faster. So in that case, it makes sense to only convert, or to only quantize a part of the model, and only quantize those layers that are a bottleneck that takes a lot of time to compute. You can only quantize those. That's something you can do. So in that case, you would have like a hybrid model that Archana was talking about. Um, so that's like a good midway. There's you can also go like a step further where you quantize your whole model and save it. But then when you load the model and then when you perform predictions, you convert that model to floating point, right? Because you have this you know what the min and max are, right? And if you just store the min and max, then you can reconvert it again to the original values. So if you do that, if you so what that will do is it'll reduce your memory footprint when you're saving the model, because you're saving the model in int8, uh, which which takes less memory. But then when you're performing inference, you can still perform inference with using the full precision, so you are not going to lose accuracy. And finally, the last thing that you can do is you can save your model in int8, and you can also perform inference in int8, which is what you would ideally do in like the smallest devices at the edge. And that is like yeah, that is where you can use the full potential of quantization. But that's also where you have the most accuracy loss, and that's also where you need to do a bit more fine tuning to regain your accuracy. So yeah, I hope that answers your question. Archana, you want to maybe add something else to that?
No, no, no. I think you covered it perfectly well and gave a quick snippet of what is coming next. So,
Mhm.
yeah, I definitely believe that we will be going through it just in case you weren't able to follow through. And Soham gave a lot of information advance. But yeah, we'll go through this again, and I'll let you know how this happens throughout the session. So, yeah, we have like, floating point values. What we want to say is that they come from -1 to 1. But in Tate, you're essentially trying to convert it to 0 to 255, which is 256 values. So just in case you can't understand what is happening, or like I hope like this is something that you can relate to in terms of computer science, or something, some sort of math you have read before. So so yeah, so we are doing two types of quantization. One is weight quantization, and then we have weight and activation quantization. So, what do we mean by that? We have dynamic range quantization, which is like which is run on hardware, which is what Soham was talking about. We have full integer quantization, which is run on CPU, HTPU, and microcontrollers. Then we have floating point 16 quantization, which is run on CPU and GPU. So, just in case you're someone who is not using this for microcontrollers or edge devices, you can still use quantization for CPU and GPU to actually reduce your computation. It's just figuring out a smart way to figure out which parts of your network actually need to be quantized. So, what are the types of quantization that are available? The choices that are available. We have dynamic range quantization, which is like the simplest form of quantization, where you are doing like post-training quantization and only reducing the only concentrating on the weights and converting it from floating point values like 32 or 62-bit to 8-bit values of precision. So why do it? You want to have like reduce latency. So on training, you focus on quantizing the weights. And at inference, the weights are converted back to 8 to floating point values, which is what I was talking about previously. And this conversion is done once, and then it's like sort of cached to make sure that we are reducing the latency. And we also have full integer quantization. So what do we mean by full integer quantization? We make sure that all model math is integer quantized, which is what Soham was mentioning before. So you can run it on hardware accelerators, where you're making sure that there's reduction of latency, reduction of memory usage, and the entire model math as such, weight and activations are quantized. And then you also have float 16 quantization. In essential, you're reducing the size of a floating point values by quantizing the weights to float 16, which is an IEEE standard, it seems. And what it does is it reduces model size by up to half, as compared to both full integer and dynamic range. It reduces the model size up to half, and it causes minimal loss in accuracy. And I think it supports some delegates. When essential, what we want to say, it is perfect for running it on a GPU. That's it. In simple words, I think. Or like, I'm not really sure if people would have heard of delegates and so on. It means that it's perfect for running it on GPUs. So in case you have like your clients or someone with expectations of reducing the model size, do look into these techniques the next time it comes up. And the optimization toolkits provides you with technique ways to go after these techniques, so you for sure can reduce your TensorFlow models or TensorFlow Lite models to this these types of quantization or quantized models as such, we can say. So, what do we mean by that? What is actually happening inside a neural network? We've talked a lot about the math, but how does it like correspond to a neural network? So, what really happens with a neural network is that we are having a lot of input values with like obviously with different variables that we have written here. And in essential, what we're trying to do is that we're trying to map it to an output value. For example, do classification. So, like we have an input, as I said, and then we have a forward pass in which we are calculating it to map it to an output. And then what happens is that we also have something called the backward pass, where once we calculate the weights to certainly map the input to the output, we are updating the weights back in the backward pass, which is in essential a back propagation, right? Which is like a term which is used again and again. And this is what happens during training. Right now, what happens during inference? What happens when we take the model and we deploy it to small devices? In the backward, there is no backward pass that exists. We do have an input pass and a forward pass that exists, but no backward pass that exists. So, which brings me to post training quantization. So, we have, because I'm going to be using forward pass again and again and backward pass again and again. So, I want to make sure that it's quite clear. If it's not, we can go through it again. So, with forward pass, what we have is that we are, taking 32-bit value, reducing it to 8-bit. There is loss of precision that happens here because we are converting from 32 to 8-bit, and the first thing that pops into our head is obviously we are losing precision values, and then we're converting it back to 32-bit for inference. And the example, for example, you can think about it like, you're starting with 0.2345678 in the 32-bit, and after conversion to 8-bit, it's reduced to 8-bit value. And then when we convert it back to 32-bit, let us say you got 0.235. So in essential, it's not really the same, is it? You have lost some amount of precision here. And what we realize is that a loss in precision can eventually lead to a loss or a drop in accuracy, which you don't want. You want to make sure you are reducing the model size and using less computation, but at the same time, you are not having the same accuracy drop. So, this brings me to post training full integer quantization. And basically, which I mentioned before, it's a form of full integer quantization. It enables users to take an already trained floating point value and fully convert it, like what Seshu is describing, fully convert it using 8-bit signed integers. And so we are able to reduce the numerical precision of both the weight and the activation of the model to reduce the memory and improve the latency. and it's a hybrid operation, since we are focusing on weights and also certain paths which allowed computation to take part in floating points. And what we want to do here is something very interesting, which I talked about earlier, is to make sure that we are able to assign certain layers to run in certain ways. What I mean by that is that you are able to assign certain layers of the model to run on a CPU, for example, which can handle 32-bit operations, and then you take certain layers to be run on Int8, and then you run it on an edge TPU or a microcontrollers which support like integer bit or Int8 operations. So, but at the end of the day, what we end up seeing is that you do have accuracy drops that happen over time. So, how do I prevent that? So this is where quantization aware training comes into play. This is very, very interesting, is that we do realize that a lot of quantization techniques have precision loss. But with quantization aware training, what we're trying to do is we are trying to make sure that your accuracy does not drop that much. And when we go through the collab notebook, we'll realize that we are doing quantization aware training and how the accuracy does not drop that much. But here is like giving you a quick theory into how it works. So what we want to do is that we want to make sure that we are able to deploy a model, and by retaining close to the original accuracy, as mentioned before. So what are the problems with quantization? We realized we're going from higher precision to a lower precision, so it's lossy in nature. You're rounding off values, as I explained, so you are losing you are losing out on precision. And there's accumulation of loss. What I mean by that is there are three types of loss which we come into play. There's information loss. So when you go from higher precision to lower precision, you're losing out on important information, um, important information that the model can learn from. You're losing out on that. There's computation loss, because what happens is that going from higher precision to lower precision, you're essentially doing mac operations, because at the end of the day, all neural networks comprise of is multiply and accumulate. Now imagine you have a loss that occurs in one stage, and then again you're doing multiply and accumulate operation. You're is in essential you're actually increasing the number of computation loss you might have. So that happens, and all of this means that we're losing out on precision, so it is a form of rescaling loss. So to prevent all of this, we came up with TensorFlow came up with quantization aware training, where the core idea is that QAT simulates like an environment with low precision inference time during the forward pass of training. So we're converting the floating point value to low precision bits, and we are converting the low precision bits to higher bits again. And what we want to do with quantization aware training here is that we want to make sure that during training, we are making the network learn of the loss. So now, get like understanding quantization aware. What I mean by that is that your model in essential is able to already understand that, okay, if this is what my quantization loss is going to be, then I will learn that from the start. Is that understandable? I hope that makes sense. What I mean by that is like we take the weights here, we add quantized weights to the model. So now, after we add quantized weights, we then do the convolution operation. So your model has already seen what happens when you are quantizing the weights. It is not something that happens out of the blue. So it is quantization, like in some ways aware of what happens when you quantize the weights while training. And what happens while doing this, although like it seems so superficial on top, it's actually quite brilliant, right? You're able to already teach your model that, okay, if I have this certain loss that occurs, I'm going to teach you that from the start. So when the model actually is quantized, it's able to retain the same accuracy and is able to retain the same information, because it does not go through the entire it is not losing out on the entire information. So this is what we use for quantization aware training. And so let me smooth this here. Yeah, so during the forward pass, what we're trying to do is that you again, like, going through the input is mapped to an output in a neural network. So now in the forward pass, we are quantizing the float point weights, and then we are training. Once we quantize the floating point weights, we are then training, and then we calculate the loss, which is again in floating point values. So now essentially in the backward pass, we take this, it remains the same and it updates the weights in floating point values. So only in the forward pass during training are you converting the weights and quantizing it. I hope that, or you're introducing, let us say, quantized weights onto your network. I hope that was understandable. Then what we notice now is that we have like different models. So we have like something that we will go through in our demo today, and you will see this happening real time too, but I'm just giving you a very high level information here. We have different sort of models, and they have floating point baseline model. Let us they say that they perform like this with floating point values. What we realize is that if we do full post training full integer quantization, which is what was even suggested by Seshu, right? You're taking the entire model and you're quantizing it, we actually lose out on accuracy. You can compare it. Look, compare this to this. You can actually see we are losing out on accuracy. But with the QAT model, we see that we are able to maintain the accuracy closer to the original. So this is what we will be seeing in the demo today. So Soham, over to you.
Yeah. So thank you so much, Archana. I think before we start, maybe we should wait and see if people have any questions, because like that was like a lot of information, and I'm sure like people will have some questions.
It doesn't look like anyone has questions right now.
Okay. Okay, in that case, so I just posted a link to the collab notebook in the chat. So you won't be able to edit that collab notebook, but what you can do is you can copy that notebook over to your own, Google Drive, and then start using collab from there. Um, so I hope you can see my screen.
Yes,
And
we
how
can.
you can actually do that is you can click File, and you can click Save a Copy in Drive, and this will save a copy of this notebook into your drive so that you can start using it. Yeah,
Okay, I
I
guess
think
we
we
have
have a
one
question.
question. It is
Yeah.
needed a lot of, will there, oh yeah, it is a lot of information. I'm sorry, we are talking a lot about quantization. I will make sure that, yeah, the recording will be available. If you can join our Slack group, I will leave the Slack link right now, and you can join in our Slack group, and you can maybe like we will post the recording there.
Yeah.
I hope that answers it. Yeah.
Yeah, and also the Slack group is like, I really wish all of you like really use the Slack group a lot, because we are like really active on Slack, and we keep trying to help people out. So if you have any questions, like seriously, night or day, just like message us, and we'll definitely get back to you with answers and maybe even more resources to help you out. Yeah. So I just started running this notebook, just so that we have some results while I explain it. So the first thing we need to do is we need to install the TensorFlow model optimization framework. So we can do that by with the first line, which just installs it. So then we have to so this is all standard Python stuff. You should know this. So we import the things we need. Yeah, and then so for this we'll be using the Keras. So we'll be using Cypher 10 from Keras, and we can use this from Keras to kind of load the data. So it'll download the data into this node environment, and yeah, we can plot some of the data. So CIFAR 10, like the images are a bit blurry, they're a bit weird, but that's okay. We'll still try to see if we can classify some of these images. So yeah, So before classifying, we always normalize our images. So I'm just going to divide by 255, just simple normalization. Then convert everything to categorical and create a model. So for this, I'm not using like a pre-trained model like MobileNet or something, even though we can, or like Inception or something else, because I want to be able to show you the comparison of using a technique like this across the different styles of quantization. So what are the results if we quantize do post-training quantization or quantization over training. I want you to be able to see that, and it helps to do that on a smaller network, so it's faster as well. So yeah, so this is like a simple network. It has two convolutional layers, and average pooling layers after them, and then two fully connected layers with so the first one has 64 neurons, and the second one, which is the final classification layer, has 10 neurons. Um, and yeah, so we train the model like normal, and we get an accuracy of just a bit less than 65%, right? Um, so yeah, now what we're going to do now is we're going to use the TensorFlow model optimization toolkit, and we're going to quantize the model. Um, this will create the same model, but it will create it in a quantization aware. It'll create a quantization aware version of the model. Um, so what's the difference between a normal model and a quantization aware model? So the main difference is so the layers, right? They get converted to their quantized equivalent, right? So instead of having a conv2D layer, we'll have a quantized conv2D layer that looks something like what Archana showed before. Um, it looks something like this. So instead of a normal quantizing layer, instead of a normal convolutional layer, this in a quantized convolutional layer, we'll quantize the input weights, right? And we'll also quantize the outputs. And the good thing is, Keras kind of handles and TensorFlow handles all of this on its own, so you don't need to do anything. All you need to do is just create the model as a quantization of the model. And yeah, so once we have this quantization aware model, we can retrain it. And so yeah, it's still training, but just give it like a few seconds. And what we'll see is like this model will have a very similar accuracy to our previous model. Um, so also, like, I'm not changing any of the other hyperparameters here. So I'm training it for the same number of epochs. My batch size and everything is same. The only difference is that right now we're using a model that has these quantized operations. So yeah, so our quantization, so our testing accuracy is about 63%. So there's like a 2% drop. That's kind of expected, but that's not a lot, considering that now we can actually perform inference faster. So let's kind of see those results. Yeah. But before that, we have to like convert our model, our quantization aware model, to TensorFlow Lite. TensorFlow Lite is the is what is used to kind of quantize our model, and what is used to like create these binaries of models so that they can run on smaller devices. But TensorFlow model optimization toolkit is what actually does the quantization. Sorry, TensorFlow model optimization toolkit, it doesn't do the quantization. It just creates like the quantization aware model and trains it. And so this model right here, this accuracy that you're seeing, it's still using floating point weights. It's not actually quantized. It just has layers that can be quantized later on in a better way. Right? So okay, so TensorFlow Lite also has a few quantization methods. There's default, and there's also two others that we'll see that optimizes for different things. Default is just like the default optimization method that then there's others as well that for instance optimizes for lesser space or optimizes for faster inference, and we'll see those like at the end of the notebook as well. So this is just a normal function that just evaluates the model and gives us the accuracy. Um, okay, so how do you actually do an how do you actually perform inference using a TensorFlow Lite model? So you have to kind of load it into the TensorFlow Lite interpreter, which is what we're doing here. And then we can evaluate the model's accuracy. So the model's accuracy is about 62.77, which is actually, yeah, which is like 0.1% less accurate than the model's accuracy when we were using floating point, right? So that's actually amazing if you think about it, because we're now using int 8 weights that have 4 times fewer precision, but it's still like it's just 0.1% less accurate. um, but what happens when we try to quantize the normal model? So the accuracy drops by 1%, right? And that's a huge drop. So so yeah, so that's oh wait, my bad. This is actually not the quantized model, because we haven't actually quantized it yet. This is just like this is also the floating point model, but we're just using the TF Lite interpreter to perform the inference. Um, but yeah, yeah, so the accuracy is still kind of like similar, even if you use floating point. Um, so if you use TensorFlow Lite without quantizing, the accuracy is kind of similar. And finally, we can save the model. So let's see. Yeah, so you can see how the quantized model, it takes lesser memory to save as compared to the normal model and the TF Lite model that has not been quantized. Uh, so if you multiply this with 4, you should get something around this value, which also shows that we're like reducing our precision from FP32, which uses 32 bits to save the models, to int 8, which uses 8 bits to save the models. So yeah, I hope that kind of gives you an overview of the TensorFlow, how to use TensorFlow model optimization toolkit to quantize your models. If you have any questions, I guess like we can like take them up now.
Yeah, we
Archana,
have
are there
one
any?
question. Before we
Mhm.
get into that, I just want to say that what we realize here is that when we quantize the model, like firstly, when we just use like without quantization, when we just use a normal TF Lite model, we can still see that the model occupies a lot of space. And if you have like a 1 GB, RAM or 1 GB memory that exists on your device, and your device is really small, you have to make decisions that, okay, I can only partition this much space and allocate it to my model. And I want other rest of my space available, maybe for data, maybe for other functions. Maybe you need to take this and send the information. Maybe you want to put some network protocol out there, and the protocol is also going to take up some space on the memory. So you have to make decisions at that point of time that, okay, how do I allocate my space? And that is where quantization plays such an important role, right? Not only in that, like for example, like I was thinking about it. So like in my workplace, we have less compute to use, because we oftentimes will be sharing our compute with other folks, right, at in the office. That happens a lot, right? And how do you make sure that you are able to utilize your compute to its best use. So I think that is where also quantization comes into play. If you feel like your network can be quantized and accuracy, a 1% drop or a 2% drop in accuracy is something that won't affect you a lot, so you can definitely get into that too. I hope
Yeah,
that was understandable. I hope that makes sense. We also have a few questions that came up. Can a regular TensorFlow model, which has already trained and saved, be converted to TensorFlow Lite model?
yeah, absolutely. And that's one of the like
Mm.
really great features about TensorFlow Lite. So as long as you've trained a model using TensorFlow, you can convert it to TensorFlow Lite and quantize it.
Hmm. Okay, and then we also have Seshu asking, can the model be saved into TF model as well as TF Lite model? Before using TF Lite model converter code, can it be saved as regular model?
Oh yeah, for sure. Yes, it can.
Okay. Let us know if you have any other questions. Like, feel free to ask questions, not be someone who does not ask us questions, because we know that during this process, it can be a lot overwhelming and we gave you a lot of information. So, I definitely realize it will take some time. We have another question. Which element in your model results altered you to deciding to process quantization instead of fine tuning other parameters? That's a very interesting question. I think, like, what do you decide between fine tuning other parameters or quantization? I think like there are like it's an abstract level question, at least for me, because I know there are several ways that help you go where you need to go. But what I realize is that if your end goal is to have a smaller model size, if your end goal is to have a small model running somewhere, quantization is a for sure method to go after. Like, that's the first thing you go after if that is needed. But I mean, if you have to fine tune other parameters, I'm not very sure if it can result in a smaller model size. So, what are your thoughts here?
Yeah, absolutely. So there are some things you can do to your model to reduce the model size. For instance, you can change if you have like a really large dense layer with a lot of neurons, you can reduce that. Um, you can have convolutional layers that uses fewer kernels, but those will dramatically affect your accuracy, and it won't really and it might not affect your inference latency as much. But if you quantize your model, then your inference latency can get reduced by a lot. And um, and and, uh, and like we showed, your accuracy drop is not going to be much either.
And we have another question. Thank you so much for, keep your questions coming, because it really helps us to know whether or not you got it. And if you didn't get us to, and you don't want to ask us questions right now, we can make sure that we do it after. You can post it on Slack. We'll make sure that we answer it. So feel free to ask us questions, and if you're hesitant, feel free to reach out to us again and again. Do we have to convert the original model to a smaller model using TensorFlow Lite, depending on what hardware we are using?
Right,
Um,
yeah, and I think I didn't explain that part really well when I was showing the demo. TensorFlow Lite is like is this wrapper that is used to uh, run quantized models. Um, so if you want to use quantized models in TensorFlow and you want to um, you want to use quantized models, you have to use TensorFlow Lite to run them. So yeah, you have to convert your original model to a TensorFlow Lite format if you want to gain like the full um, advantage of using the quantized model, because TensorFlow Lite has this thing called the TF Lite interpreter, which is like this really fast uh, like toolkit. I'm not sure if toolkit is the right word to use, but basically it's like this interpreter that executes your network really fast, and that is also a part of what gives you like this advantage of like this the advantage of using quantized models. Yeah.
I think we can move on to the last bit.
Yeah, I know we're running a bit short on time, but if or I think we've kind of way past the time limit, but this is something that I'm like really interested in. This is another type of quantization that's not really that popular, but it's still really powerful. It's called dynamic fixed point quantization. Um, so normally what happens is in a when you quantize your network, you're using int values, which are which can be from minus 128 to 127, um, right? um, and despite what you like you can create techniques to reduce your accuracy drop or and all of that, but at the end of the day, you're not solving the main problem, which is the fact that you're still using integer values, and integer values aren't really that great at um, at at representing weights. Another problem with integer values is that integer values are usually from minus 128 to 127. Integer values are usually in that range, but neural network weights are usually in the range of like minus 1 to plus 1, and you might have some weights that are like in the range of 2 to minus 2, but most weights will be centered around 0 with a deviation of 1. um, so given that, um, if you take something that is where like just even tiny differences in values can change your accuracy a lot, and then you're blowing it up, and you're putting it in a range of like minus 120 to 127, that's going to cause a lot of issues. Um, so there was these researchers who came up with this thing called dynamic fixed point quantization. And and what they do is really simple. Like, don't let this formula like confuse you. But what they do is, they specify this value called the fractional length, which I'll be referring to as the DFP value. And using this DFP value, they actually they can scale down the range of of these of intake values in special hardware. Um, so what does that actually look like? Um, so it looks something like this. So when your DFP is 0, we have our normal we have our normal intake values which go from minus 120 to 127, and the precision is like in one, like the numbers decrease by 1 or increase by 1, right? So we have minus 127, then minus 126, and so on. But if we if we if we use a DFP value of 1, that is essentially kind of like having a floating point value, um, and we are shifting it like this towards the left, uh, and we're using some bits as a fractional bit. Um, but what it does is, it divides our min, our low, and our high by 2 to the power of our DFP value. So in this case, 2 to the power 1, which is 2. So our low now becomes minus 64, right? Minus 128 by 2, which is minus 64. And our high is minus 60, like 127 divided by 2, which is 63.5. So in this case, we can actually keep that point value, um, because we can now handle decimal points, right? Because because even though we are still performing our computation on int values, we can now store this DFP value, and we can then convert our int values into this value by just dividing it. So this can now be handled in the hardware basically. Um, but the advantage of this is now we're getting more precision.